Alright, here's Lab 5, Physics 2211 by Landon Hicks. Alright, lab goals and principles. So the goal is to determine the amount of drag it takes to stop a card I throw using Newton's second law. The principles, of course, Newton's second law, F net equals ma. The position and velocity update formulas, xf equals xi, plus the average velocity times the time, then the final velocity equals the initial velocity times the acceleration times time, which of course acceleration we can sub for F net over m. Alright. So, I should have showed you all the video through editing. So here's the data from that video using the tracker. I'm really only concerned about the X position only because it stops midair before it reaches the ground, which is why I'm not really all that concerned with the Y position. As you can see, at about 0.8 seconds here, it goes and it reaches a peak and then it stops, travels backward actually. So we're going to calculate the amount of net force it takes for it to stop, but in the video, that's why I'm only concerned with the X direction. Alright, so here's my glow script code. So I used a lot of the principles from Lab 1. So I go in here and I calculated the net force that I would need so I can get another graph on how it would look for the X direction of this throwing card. So if I go in and I change my F net vector in the X direction by 0.028 newtons, then I'm going to go in my velocity. It's going to be F net over the mass times delta t. So every time it moves through, it'll multiply it by that, and then it'll change my position based on that. As you can see in the graphs, the position is a concave line, which makes sense because it's a constant acceleration. Well, I'm simulating constant acceleration. That is negative, so it makes sense that it's concave down, and then the velocity is decreasing, meaning there is an acceleration and a net force. Alright, so work to derive drag. So we're given delta t. My thing kind of messed up. It started about 0.5 seconds, ended at about 0.8 when it reached its max, or its VF equals 0. So that took about 0.309 seconds. My V average, which I took my initial velocity. Well, I took the amount of velocity it would take to traverse that amount of x distance in that time. It would be 2.74 meters per second. And then delta x was about 9.91 meters. So, V average, of course I got that by doing VF plus VI over 2. VI equals 2V average minus VF. So we can then look, VI is going to equal 2 times V average, 2.274 meters per second, minus, of course, it stopped at 0, so it's going to be 5.48 meters per second. And then once we have our initial velocity, we can then calculate our acceleration. Our acceleration's going to end up being the final velocity minus the initial velocity over the time, which will be about 0 minus 5.48 divided by 0.309. Give me us negative 17.73 meters per second squared. This makes sense because it's stopping in a very short amount of time. The whole video only took about 2 seconds, the throwing portion of that being about a third of a second. So it makes sense that it's that fast of acceleration or deceleration. So the F net is going to be ma, right, which is equal to the drag, but that's the only force in the x direction. We're not accounting for the y velocity. So we take the mass of the card, which the average is about 1.6 grams in kilograms. It's 0.0016 kilograms. Times our acceleration, we're going to get about 0.284 newtons. So is this reasonable? I would say it's reasonable because drag force is so low because the mass of the playing card is incredibly low. So even though the initial speed is pretty fast, I mean, in order for it to take a third of a second to go about 9 meters, that's really fast. The mass is so low and the momentum is so low, it's going to take a very small amount of force. And, just for fun, I looked up what's the average output of force by high five. It's about 6 newtons from what I could find online, which is kind of funny because, if this is about 0.028 newtons, most people won't be able to notice that, which makes sense because most people can stop a card without noticing it. So thank you for your time.